Welcome to Variational Principles and Lagrange's Equations, a discussion based on the second chapter of Herbert Goldstein's treatise, Classical Mechanics. Today we are going to be discussing Hamilton's principle. Previously we have seen that D'Alembert's principle leads to Lagrange's equations by considering the instantaneous state of the system and virtual displacements around it. It is an example of a differential principle. One can also consider an integral principle, which involves the entire motion of the system between two moments in time, t1 and t2, and variations of the whole motion. To this end, we need to define two important concepts. The first one is configuration space, which is given by the n-dimensional Cartesian hyperspace, where each point is characterized by the values q1 through qn of the degrees of freedom. And the second one is the path of motion, which is the curve traced within configuration space between two moments in time. Configuration space paths and real trajectories needn't necessarily hold any resemblance, just as generalized coordinates needn't necessarily resemble Cartesian coordinates. Hamilton's principle applies to monogenic systems, that is, to systems for which the applied forces are derived from generalized scalar potentials depending on coordinates, velocities, and time. If the potentials are only position dependent, then the systems are conservative. Hamilton's principle regards the quantity known as the line integral or action integral given as follows. The integral between the moments in time t1 and t2 of the system's Lagrangian defined by the difference between kinetic and potential energies. And what the principle states is that the motion of the system between these 2 points is such that the line integral has a stationary value for the actual path of motion. That is, the integral along the correct path has the same value within first-order infinitesimals as that along all neighboring paths differing by infinitesimal displacements. In ordinary calculus, this is equivalent to the vanishing of a function's first derivative. Effectively, we are seeking functional forms that minimize the path integral. Formally, this is written as follows. For the correct path, the variation of the action integral will be equal to 0. So that is, the integral itself will have an extremum value. The above is the necessary and sufficient condition required to obtain Lagrange's equations for holonomic systems. Thus, the mechanics of monogenic systems has a deeper grounding in Hamilton's principle as opposed to Newton's laws of motion. One advantage of this approach is that the equations of motion always have Lagrangian form, regardless of the set of generalized coordinates used to express L. More importantly, non-mechanical systems can be treated within the framework of classical mechanics by this approach. In other words, this is the standard approach used in the classical theory of fields. To summarize this short but very important discussion, we have defined formally the meaning of configuration space, path of motion, and monogenic systems, and we have stated Hamilton's principle for monogenic systems as a deeper grounding for classical mechanics in terms of the action integral. In the following, we will develop techniques for the calculus of variations. Thank you very much for watching the video. I hope you found it worth your time, and I will catch you later. Goodbye.